Okay, last time we talked about the common ion effect, and what we're going to talk about now is really just an extension of that. We're going to talk about buffer solutions. So a buffer solution will happen when you have a weak acid or a weak base, and in that same solution, you also have the conjugate of that weak acid or that weak base. So if we have a weak acid, we need the conjugate of that weak acid. If we have a weak base, we need the conjugate of that weak base. And when we get that, we get what we call a buffer solution. And so we actually saw these solutions in the previous video, where we were looking at the common ion effect. And so one specific case of the common ion effect gives us a buffer solution. And so if we have that conjugate of the weak acid or the weak base, we get a buffer solution. We have to have both. Just having a weak acid does not give you a buffer solution. Just having the conjugate of a weak acid does not give you a buffer solution. You have to have basically a significant amount of substance from each side of that equilibrium for either the weak acid or the weak base. And so you need some of the weak acid and some of its conjugate, or some of the weak base and some of its conjugate. And when we have a buffer solution, what ends up happening is that that solution has the ability to basically resist change in the pH when we add small amounts of either acid or base to that solution. It doesn't mean the pH isn't going to change at all, but what it means is that it's not going to change very much. And relative to how much, say, a beaker of water would change, it's almost no change at all if we have a buffer solution. And so we use these solutions in a lot of different ways, one of which is to just keep a pH, a constant pH during some kind of reaction. If we need to control that, there's also a very important buffer solution in your body. It's called your blood. Your blood is buffered, and so it keeps a very constant pH. If it didn't, that would be pretty problematic. And so buffers can be really important for us to control the pH of whatever it is that we're looking at, whatever the solution is. Okay, so let's look at an example here. In our discussion of common ion effect, we looked at acetic acid and a solution of acetic acid with sodium acetate, and we dealt with it in terms of what was happening with that equilibrium. But let's look at it very specifically now in terms of what would happen if we had an equimolar mix of acetic acid and sodium acetate. So I put in the same amount of each of these two substances into my solution. It doesn't really matter what that amount is, we're just going to say we have the same amount. And so we're going to see what that ends up doing to the pH here. So the equilibrium that we're concerned with is that weak acid equilibrium of the acetic acid. So we've got acetic acid here in equilibrium with the acetate ion, and then we get that hydronium ion as well. And so this is the equilibrium that we're really dealing with. And so if we have an equal molar amount of these two substances, what that means is we have a substantial amount of each side of this conjugate acid-base pair. And so that means we're going to have a buffer. Okay, so we don't know what the amount is, we're just going to call it X. So we have X amount of acetic acid, X amount of the acetate. Our hydronium ion, if we haven't dissociated any of the acetic acid, will be somewhere in the vicinity of 1 × 10⁻⁷ if we're at 25 degrees Celsius, because that's what we get just from the autoionization of water itself. And so let's see what happens if we were to add a small amount of a strong acid. So effectively, we're just adding hydronium ion to the solution here. So if we add a small amount of hydronium, what that's going to react with in our equilibrium is it's going to react with the base form, right? So remember, the acetate ion is the base form. The acetic acid is clearly the acid form. And so if I add some hydronium ion, I'm going to react with the base form of this compound. And so that H plus is going to react with some acetate. It's going to create acetic acid. And basically we're back into this equilibrium that we dealt with already. And so you're going to have basically a creation of some extra acetic acid by adding that H plus. If you have extra acetic acid, that would be like adding a reactant to our equilibrium. And what that's going to do is it's going to shift our reactant or shift our equilibrium towards the products. And we're not going to change this H plus concentration very much at all. We've added H plus to the solution, right? But there's enough of this acetate ion in there to basically completely react that H plus that we added from the strong acid and create the acetic acid, and then we're back into this equilibrium, okay? And so while the hydronium ion would change a little bit, it really isn't going to change very much even when we add this strong acid to the solution. Okay, so our pH is going to stay relatively constant. It's not exactly the same. It will have an effect. The pH will change a little bit, but it's not going to be changed nearly as much as if we had added this to a regular solution, a neutral solution or something like that, or something that didn't have a buffer in it. Let's consider what happens if we add a little bit of a strong base. So we add a little bit of hydroxide ion to our solution. So hydroxide is a base. And the question becomes, in our solution, what is it going to react with? Well, there's not enough hydronium ion for it to react with, so that might be your instinct. What it's going to react with is the acid form of our compound. And so the acid form will react with that hydroxide. So all of the hydroxide will react with the acid form. It's going to create some acetate ion and some water as well. But effectively what that does now is it adds a little bit of extra acetate ion to our solution. It's going to drive our reaction back to the left a little bit because we have a little extra acetate now. And what that ends up meaning is, again, our hydroxide and our hydronium ion concentration don't change a lot from where we started. They're going to change a little bit, okay? The pH is going to change a little bit when we add a strong base, but it's not going to change nearly as much as if we had added that to a solution that was not a buffer solution. Okay, so this is kind of a cartoony version of what would happen, and it's not exactly right because the buffer would change a little bit. But if we sort of compared what would happen to the pH of a solution that was just water as we add hydrochloric acid to it, that water solution would start at 7, right? And then it would drop pretty dramatically until we got to whatever that concentration of the HCl would be and would give us in terms of pH. So pretty low pH, around 1, something like that. A buffer solution, on the other hand, is going to stay relatively constant. Now, this is a flat line. It's completely flat, and that's not quite right. The pH of the buffer would drop a little bit as we're adding this HCl, but it would stay relatively constant. And so if we're trying to control the pH of a solution, a buffer is a really good way to do that, to build a buffer that has the pH we want it to have, and that way as reactions take place and a little bit of hydronium or a little bit of hydroxide are introduced into the solution, it doesn't change the pH very much, and this can be really important. Now, a buffer solution can be overwhelmed. You can't just keep adding HCl to that solution forever and have it stay constant. And the reason it can be overwhelmed is because you only have so much of that reactant and that product, of that weak acid and that weak base, that conjugate acid-base pair. And so eventually if you use up one of those two things, either the weak acid or the weak base, you will eventually overwhelm that buffer. The buffer will no longer be functioning, and you're going to be able to change the pH pretty dramatically. So if you add enough HCl, you'll use up the base form that's in your buffer. If you add enough OH minus, you're going to use up the acid form that's in your buffer, and then you no longer have a buffer because you need both of those conjugates in order to have a buffer solution. So as soon as you use up one of the two things, you no longer have a buffer. Okay, so buffer solutions are basically just a special case of our common ion effect. And so because of that, we can use the Henderson-Hasselbalch equation that we derived earlier to figure out what the pH of our buffer solution is going to be. So again, the pH of our solution is going to be the pKa of the acid form of the thing that we're looking at, plus the log of the conjugate base concentration over the conjugate acid concentration. And it doesn't matter if you're building your buffer from a weak base or a weak acid, this still has the same form either way. And so you always are going to be putting that conjugate base concentration over the conjugate acid concentration, and it's always the pKa of the acid form that's in that buffer. Okay, so let's look at a special case here. If the conjugate acid concentration is exactly the same as the conjugate base concentration, this term inside of the log is just 1, right? And so if that term is just equal to 1, well, the log of 1 is just equal to 0, and so this entire second term disappears, right? And it just becomes 0. And in that case, the pH of your buffer is just going to be exactly the pKa of whatever the acid form is. What that ends up meaning is buffers are basically the most robust. They're the most useful when you're right around the pH that is equal to the pKa. And the reason that that's the most robust is because it means they have equal amounts of the conjugate base and the conjugate acid. And so it's going to be the hardest buffer to break because you have quite a bit of both the acid form and the base form. So when you're trying to design a buffer, what you're trying to look for is a weak acid that has a pKa right near the pH that you're trying to build the buffer for. So if you want to be building a buffer that has a pH of 4, you're looking for a weak acid that has a pKa around 4, somewhere in there, in order to build your buffer with it. If you're trying to find a buffer that has a pH of 11, then you're trying to find something, a weak acid, that has a pKa around 11. Okay, and so that's where you're going to get the most effectiveness, is if you've built a buffer that has a pH right next to the pKa of the weak acid